Today let's start with the next component of the leakage power dissipation, that is subthreshold leakage, or I can say subthreshold leakage current. So in the previous class, we started with the leakage power dissipation. So the leakage power dissipation will happen due to some of the factors, that is the diode leakage dissipation is there, next the subthreshold leakage is there, next the gate oxide leakage is there. When this leakage power dissipation will happen? When the circuit is not in the active mode of operation, like during when the circuit is in off condition. When the circuit is in off condition, there will be some small amount of leakage will be there. So that only we are studying. In that we studied so many different leakage parameter measure. So we studied in the previous classes. The one is nothing but the diode leakage, that is nothing but a PN junction reverse bias current. Then another one more is to band tunneling current, that we studied in the previous class. So now we are going into the subthreshold leakage current. So from the name only I can say what is the meaning of subthreshold. Subthreshold means less than the threshold voltage, because as you know that if I say in any transistor, the MOS transistor if I take, when the transistor will be turned on, when your gate voltage is greater than the threshold voltage, then only the transistor will be in the active mode. But when the VG is less than VT, you will think the transistor will be in the off mode. No, the transistor will not be in active mode actually. So that is the portion the devices will work for, the low power devices will call. So like a simple I can say the subthreshold leakage current will happen during when this is simple I can say as you decrease your channel length. So as you decrease your channel length, automatically your less threshold voltage also will get reduced. So or I can say whichever the devices are working less than the threshold voltage, that is low power devices as I mentioned. So but there also there will be some amount of leakage will be there. So simple I can say, so that subthreshold leakage current can see my circuit due to the carrier diffusion between the source and the drain region of the transistor in weak inversion. So simple one thing is I can say this due to carrier diffusion between the source and the drain. By short I am writing SMD. Source and drain region in the weak inversion. So when it will be happen? When the VGS is less than VTH. So this only we can say the subthreshold leakage. Okay. Now, so here the very important thing, the amount of subthreshold current may become the significant when gate to source voltage is smaller than, but very close to the threshold voltage of the device. So let us write what is the expression for subthreshold voltage. Subthreshold voltage, the expression will be I sub is equal to subthreshold B A into e to the power Q by N dash K T into Vg minus Vs minus Vth 0 minus, it's a continuation that is here, gamma into Vs or gamma dash I can say, plus eta into Vds into 1 minus e to the power minus Q VDS by KT. You see here this portion A into this 1 minus e to the power minus Q VDS by KT is nothing but the diode leakage current. So additionally we are having something here, you can see, right? So now here this is the total overall subthreshold current equation. Now here two different parameters here mentioned, that is the gamma equation. Gamma, the one is nothing but a eta, where the gamma is nothing but a body effect coefficient, then eta is nothing but a double effect coefficient, that is drain induced barrier lowering coefficient actually. So now we need to know what is the A actually here, where the A is nothing but here, this A can be written as mu naught into Cx W by L effective channel into KT by Q the whole square into e to the power 1.8. Now we can see here this is nothing but your process parameter, this whole thing. So by short sometimes I can write as beta actually. This whole thing is a beta also they can say. Okay, so now this value is nothing but your subthreshold equation. Now here we can say some various mechanisms are available, or I'll say here in this you see the graph here, your x-axis nothing but a gate voltage. This is your gate voltage, this will be your drain current. So here this graph shows that it is a ID versus VG, right? ID versus VG at two different drain voltages. Two different drain voltages. So in the sense here you can see we are having like one drain voltage is 2.5 volt, the another one drain voltage is 2. Which one is 2.5? This only. This will be VD is equal to 2.5 volt. This will be your the drain voltage is 0.1 volt. Okay, now you can see what happened. VD is fixed, right? When the VD is getting reduces, or you can see increases. See that when VG is increases, so your subthreshold will be happen where exactly in the sense you see this at this point, you can see it's a off current. See here at this point it's off current, correct? No, so but if I take simply less than this portion, you can have some current. See this portion actually we are having some amount of current is getting decreasing, then it's getting increased. I can see some of the current. This is the subthreshold, I can say this only. This portion is a subthreshold. At the same time you can see here a simple we are showing the another diagram here, that is the subthreshold leakage in N transistor. This one. Subthreshold leakage in NMOS. This diagram, right? Applying this. So now your VGS, this will be your log scale, the current I. Now we can see here subthreshold. This is your less than. So your subthreshold leakage will be like this. How it will be there? The number of millivolts will be taken of current. Now, when I go for subthreshold, so many mechanisms will be there in the sense. So here I will write. So various mechanisms will affect which affect the subthreshold leakage. which are those mechanism? First thing is, the first one is drain induced barrier lowering. Drain induced barrier lowering, by short I can say double. The second one is nothing but body effect. The third one is nothing but narrow width effect. Narrow width effect, or otherwise I can gate width effect. Next is effect of channel length. Effect of channel length and VTH roll off. Next thing is we are having the effect of temperature or temperature effect. Here the effect of channel length only will have two things will be there. Here no, in this we'll have two. The one is nothing but gate induced drain lowering. By short they will call a GDL, GADL. The second one is punch through. Okay, then effect of temperatures. So these are the variants, mechanisms we are going to study for subthreshold conditions. Okay, let us study about the first mechanism, that is drain induced barrier lowering, that is DIBL. So if I want to talk about the DIBL, so here already as I mentioned we are thinking like a short channel device and a long channel device. Like for long channel device, the source and drain regions will be separated in a far distance, right? And the depletion region will around the drain and source will have little effect on the potential distribution in the channel region. So we can say the threshold voltage is the independent of the channel length and the drain bias for long channel. So for long channel, as I mentioned, for long channel the voltage, threshold voltage is independent of channel length. The threshold voltage is independent of channel length, that is L, and the drain bias also. So but then here if I want to say one more thing, as I mentioned, the source and the drain, the distance is small, right? So there's no effect in the depletion region here actually. But what about for short channel? As the channels get reduces, what will happen? The source and the drain depletion width in the vertical direction and the source drain potential will have the strong effect on a significant portion of the device, which leads to the variation in the subthreshold leakage current with the drain bias. So as you like so here you can see the diagram. Let me show the diagram. So how it is, you can see that. So this double will happen due to what? Actually, as I mentioned, like due to the drain to not this actually. This is for Judel. Okay, you can see this. This will be your source, that is Vs is equal to 0. This is your Vd, that is Vds also I can say is 0. Then this will be gate voltage. No? So as now we can see in this is a source on the drain. So the soft punch through will happen or would be induced by drain to substrate depletion region. You can see this is the drain. Now this is nothing but the ideal condition, right? Vg is equal to 0. Now what you are doing here, Vs is equal to 0, then Vg also is equal to 0. Now the Vd will be is equal to larger, that is Vdd when you apply. So now as the threshold, like the threshold voltage will be increases, which one here, okay, when the threshold voltage will increases, when the drain voltage is increases, here it's increasing from 0 to VDD as the drain voltage is getting increases. This is for short channel devices, okay. As the drain voltage get increases, then the threshold voltage will get reduced. So that only is we can call like is a drain is induced in short channel effect. This SCE is nothing but short channel effect. Now what happened, as you increase the drain, your Vs, now you think about the potential. Your surface or your source potential is less compared to your drain potential. Like, so what will happen at the time that the depletion region will get to widen, it will go down, which will be like in the, here you can see the distance here, but you can see this distance here, very small, this one. So now I can say as the drain voltage get increases, that is nothing but the drain to substrate we are connected, correct? This will be your substrate connection. So from drain to substrate, okay, so this drain to substrate, the depletion, because this depletion region is between the drain to substrate only, right? Because this is substrate. So the drain to substrate depletion region will be gross. Here you can see gross with the more reverse bias. So now the lateral electric field in drain induced depletion region will lowers the source to channel barrier. What happened here? Allowing the more carriage to diffuse from the source to channel. This will be very small. You can see because of this drain, it will be induced. So that is why I can call this drain induced barrier lowering. Because let's see here in this place here, like I can say this is a valence band to conduction band. The electrons will move over there, very small place. And so it will allowing more carriers to diffuse from source to the channel, this one. So what will be the typical Dibble coefficient values by the change in the threshold voltage. A change in threshold voltage is minus 0.12 voltage for the change in drain voltage plus 1.2 for 90 nanometer device. This is for 90 nanometer device. So that only we can call as the Dibble effect. So because of the Dibble effect, the barrier height of the short channel devices will reduces with an increase in the subthreshold current due to lower threshold voltage. You can see here we are showing the three different diagrams over there. The Dibble will occur when the depletion region of the drain, this is already as I mentioned, right? Depletion of the drain, this is the drain, this is the source, right? Near the surface. So now three curves are showing. This is our L different values of L value, the different values of drain. Three values, right? So whenever the L is this one, you can see this. This is your length. Y-axis nothing but your length. We are saying, then this will be your current. Okay. So you see, this is nothing but your source. This will be assume this is source and this is the drain. Now first, what happened here? This figure shows that it is the lateral energy band diagram at the surface versus distance. Surface versus distance from the source to drain for three different situations. First, for curve A, okay, the L is equal to, for curve A, L is equal to 6.25 micrometer. What is the drain voltage is 0.5. So this is the, whatever the curve here we are showing, that is nothing but the depletion region. You should think in that way only. This is a source, this is a drain. You can see the depletion region how it is. For L is 6.25, drain is 0.5. Next you can see L is get reduces to 1.25. What happened? You see 1.25 micrometer. The VD is same actually. So you will have the depletion region is like this. Next you can see the L is 1.25, but the VD is increases. When you increase the VD, what happened here? You can see this. This is what I can say. So simple. This is the surface. Okay. It's coming to the surface. This is the surface area I can think. This is like, so this far away from the surface, little bit closer. This is little bit still closer to the surface. So that is why we can say in this, ideally, the double effect. Ideally, ideally, the double effect does not change the value of subthreshold slope, but does lower the threshold voltage. Same time, this I can say the curve is for IG, VG also I can take. This is your VG also I can consider. That will be your ID also I can consider. So this is nothing but, because already we introduced in the previous chapters about the double also. Just here once again here we are studying. So there it's a general, because we started with the short channel devices over there. So many short channel effects we studied over there. But here what we are doing, this central is like for deep submicron. Okay, so for deep submicron, these are the effects. Again, it will like look like it will repeat. Sometimes you may get the questions there also, or you may get the questions here also. Next is the body effect. So as we know, the body effect. What is meant by the body effect? The body effect is applying the reverse bias. Applying the reverse bias between the source and the bulk, which increases the threshold voltage, increases the threshold voltage. This is called as body effect. So applying the reverse bias between the source and bulk means your VB is very greater than 0. That is the meaning of that. Okay, when you apply the reverse bias, so the bulk, the depletion region will get wider actually when you do this. So when the depletion region gets widen, that will leads to an increase in the threshold voltage. It will because due to increase in the depletion region. So that effect only is known as body effect. So what is the threshold voltage? Because as I said here, the threshold voltage will get changed, correct? So what will be the change of threshold voltage? I'll get the equation will be, we may get Vt is equal to Vth0 plus gamma into then root of 2 phi b plus Vsb minus the root of 2 phi b. So this is the surface, that is the barrier potential phi b. The Vsb is nothing but the voltage between the source and the bulk. Then Vth is nothing but the flat band voltage. This one is flat band voltage. This will be changes in the voltage. After, like a simple, I can say here, the gamma is nothing but your body effect coefficient. This is simple. If gamma is equal to 0 means if there is a no effect, automatically there is no change in the threshold voltage. Correct? No. If gamma changes, if this value get changes, then automatically the threshold voltage also will get changes. See that we are showing the graph for the body effect. This will be your various gate voltage. This is the gate voltage, right? Then this will be your drain current. The drain current will be like it will be in terms of very small current. Now we are applying different the substrate voltage, that is V sub, right? Substrate V bulk is very less than 0, is going more and more 0, means first you start from 0, minus 1, minus 2, minus 3, minus 4, minus 5. You see this, first you think your substrate voltage, this will be your is equal to 0, but it is 0. When you are increasing your gate voltage, automatically the drain current also will get increases. But you can see what happened when the V supply is greater, means 0, next is going minus 1. When it goes minus 1, your drain current is reduces. See this, drain current is reduces, at the same time your gate voltage, see this is the gate voltage, drain current increases. Again you see this substitute minus 2, this is 0.1, minus 1, this is minus 2 still. You see still, you can see what happened. So keep on your ID gate reduces, the drain currents get reduces these two. So see, you can see whatever the line length, this will be your subthreshold here. You can see this subthreshold actually, what happened, as your bulk increases, as the bulk voltage increases means more and more negative, then your drain current is getting reducing. This is called as body effect, but we can have some of the equation also over the body effect here. So like simple, it's a gamma, right? So what is a gamma actually? So the gamma is a body effect parameter. So already we written in the previous classes what is the gamma actually. Then phi b, where the gamma is nothing but epsilon Si q n a. Actually this is nothing but your gamma parameter. So now what I will say here, then what about phi b? That is nothing but what about the phi b? The phi b is nothing but a bulk barrier potential, right? This is phi b is nothing but barrier potential. That is like I can say that will be kT by epsilon natural logarithm of Na by Ni, where Na is a doping density in the substrate. So this is like the phi b is nothing but what? It's a difference between the Fermi potential and the intrinsic potential in the substrate. Now the change in the voltage, or I can say the change in the threshold voltage with respect to the bias, that is Vth divided by dVbs, that is bulk to source, right? Respect to the substrate bias. This rubber is, I can say, that is epsilon Si QNA divided by 2 times of 2 5B plus VBS. This will be the root divided by Cox, where Cox is nothing but a oxide capacitance. So as you know that already written, the Cox will be is equal to epsilon ox by T ox, where epsilon ox is nothing but epsilon Si into epsilon I intrinsic divided by epsilon naught into epsilon I divided by T ox. So this and all we discussed earlier only. So the substrate sensitivity is higher for higher bulk doping concentration, and it will be decreases the substrate reverse bias increases. So previously I written the subthreshold equation current, correct? So you can consider that equation, that also we have to consider here. Next effect. The next effect is nothing but the narrow width effect or gate width effect. Narrow gate width effect. So narrow gate width effect means what? So simple. Earlier we seen LW, right? And now just you assume as the length of channel, the width of the source and trace. No. Now make reverse way. Okay. So narrow gate width means whatever you are having a length of your channel, no, that will be your width of the gate also. So the narrow width, if you are having a narrow width, then we can see here the gate width is, this is the gate width. Then what will happen? Your threshold voltage. So for variations in the threshold voltage with the gate width for different body biases, this all are monitored. This is for body bias, that is VB is equal to minus 5 volt. This is for VB is equal to minus 4 volt. Okay, like this. So VBS. So body to body bias voltage. Now as the VBS increases, what happened? See here, as the VBS it is get increases, you can see here the threshold voltage also will be increasing. But you can see this will be your gate width. So this is the gate width is increases. Gate width very minimum means less than 1. You can see this one. Gate width is less than 1 micrometer. See, that is your gate width is less than 1 micrometer. What happened here? You can see this. So the width of the gate, particularly when it becomes narrow, it will affect the threshold voltage. So here there will be a reduction in the threshold voltage. See this in this diagram, you can see here there will be a reduction in the threshold, leads to increase in the subthreshold leakage. So I'll make a point, the reduction in threshold voltage leads to an increase in the subthreshold current. This is nothing but your narrow width effect. Next, let us go for the VTH roll-off, that is threshold voltage roll-off. As the channel length reduced, the threshold voltage of mass decreases. Right? As the channel length reduces, as the what will happen? The threshold voltage of metal, that is a MOSFET, will be decreases. So that reduction of channel length is known as VTH roll-off. Now you can see this figure shows that the reduction of the threshold voltage, the channel length, you can see here, this is nothing but your channel length. Okay, so now you can see this portion, this is VDS is low here, you can see where VDS is low. sorry, this is VDS is, the line is VDS is low, the dotted is VDS is high. So this will be your less drain to source voltage. This will be the high drain to source voltage. Now we can see what happened here. As the length increases, this is what length, okay, as the length increases, what happened here? First, the VDS is less VDS. What happened? The threshold voltage is increases, but we can see the VDS is high. When the VDS is high, so as the length is increases, the threshold voltage, see, but here you can see the threshold voltage will be here, but you can see this here, the threshold voltage will be here. The portion stability, right? Say example, when it starts to conduct, you can see this portion's threshold voltage you consider 0.7, this you consider 0.5. So as the VDS is less, so simple I can say, okay, VDS is also less low voltage, this is high voltage. So your threshold voltage get reduces. That to only we can call this threshold voltage roll off. Okay, now let us see one thing. Here, the one more diagram we are showing over there, that is the charge sharing model. See here, this will be your L, okay? This is your length of the gate. But this will be your L dash we given. Means what happened here in the sense this portion is nothing but you can see this as you increase your gate voltage. What happened? This will be your channel will look like it's in the trapezoid structure in trapezoid form actually. The new channel length. Correct? No, this will be gate length actually. This is the gate length. This is nothing but your width of the depletion range. Width. You can see as the channel length is increases. This is what they said. See, as the channel length is increases. What happened as the channel length increases? Then you will get the channel L dash, the new dash like so. The trapezoidal form very better. Next, the effect is nothing but the temperature effect. So, like effect in temperature, what will happen? Like there is a strong dependence of threshold voltage on the temperature actually. So, as the so you see this figure, I think you will get properly the temperature, then current you can see. Okay, so this one is the x-axis is nothing but gate voltage. Sorry, the x-axis is nothing but okay, VDS. Okay, now you can see there's the temperature. You can see this minus 50%. As the temperature get increases, but you can see here, I can see in this table only you can will get it now. As the temperature increases, minus 50, minus 50, 0, 25, 30. What happened here? Current. Current is decreases. So simple, as the temperature increases, then your drain current will be get reduced. Subthreshold leakage will be increases. The leakage will be more. The leakage will be more. This is what will happen. So the variations of the drain current you can see. So for the VD is equal to 2.7 volt for the drain current. This is actually You want to know what is this? This is nothing but a technology actually. What is a technology? Or L I can say. Technology in the sense in terms of here it is like technology, okay? This is point 5.3. This is like this place is point 0.3 micrometer technology. So for point 0.3 micrometer technology, the subthreshold, the current will be from 58.2 to 81.9. Okay, 81.9 millivolt per decade. As the temperature varies from -50 to 25. See, you can see this only. As the temperature increases from -50 to 25, the subthreshold current will be 58.2, 81.9. For which technology? For 0.3 micrometer technology. So now we can make the observation from the graph. So what is the observation we can make in the sense? The first observation we can make it as the subthreshold current, okay, or slope I can say. The subthreshold slope linearly with the temperature. Second one is the threshold voltage decreases. The threshold voltage decreases with the temperature at the rate of 0.8 millivolt per degree centigrade. This is nothing but the temperature effect. Next, the parameter is nothing but tunneling through gate oxide. Tunneling through gate oxide, what will happen actually, you can see when you are reducing the channel length. If you reduce the channel length, then automatically we need to reduce the oxide thickness also will get reduced. If the oxide thickness is reduces, means the oxide thickness in the sense directly in the sense like your oxide thickness means so as you know clearly, right? This will be your we are showing the MOSFET in the three regions, no? This is nothing but your unbiased region, okay, or I can say it's accumulation region, okay. So second is nothing but your okay, second is nothing but your accumulation region. Third one is inversion region. We might have seen. So this will be your Fermi level. This is like your this is nothing but your top is vacuum actually. So here we'll have the conduction valence band. So here we'll have the conduction from Fermi level. So it will transform. So this will be your semiconductor part. This will be your gate side part. This will the portion. This one is nothing but your TX. Now, so the device scaling. So normally, as I mentioned earlier, they can do the some device scaling, right? So now the device scale will raise to device scaling. Means already we talked about TX scale, TX how we can scale, and the length also we can scale, width also like that, right? So device scaling will leads to the reduction in oxide thickness. Oxide thickness, which will leads to increase the increases in the field across the oxide. So automatically what will happen? So there will be a problem like there is a tunnel through the gate oxide actually. right? So the high electric field will, along with the low oxide thickness, leads to tunneling the electrons from the substrate to the gate actually, because there will be two different electric field will be there. One is lateral field, another is longitudinal field. That is horizontal field and the vertical field. When I talk on the vertical field, actually the current will move, or the electric field will move from the substrate to the gate. Substrate to the gate, if is going intermediately, you are having the insulator, that Tx is there. That is the oxide thickness. So what will happen due to this, the thin oxide thickness, because as I mentioned here, reduction of the oxide thickness, what will happen, the more and more when you are applying the gate voltage, when you are applying more and more positive the gate voltage, automatically what will happen, so it will tunneling of the electron from the substrate to the gate and vice versa to the gate. So that basic phenomenon of the tunneling only will be like with the help of what, due to the heavily doped N plus. So simple I can say, right? Or I can write in this way, due to high electric field, due to high electric field along the low oxide thickness, leads to tunneling of electron from the substrate to gate and vice versa. Like it will be like with the help of doped, which will be doped here with the help of N plus polysilicon gate and a p-type substrate. Because of the higher mobility actually, right? Because of the higher mobility, the primary electrons will take part the tunneling process actually. So this is the figure we are showing the energy band diagrams actually here. So what is the expression for the tunneling is like Ix, that is oxide thickness, will be is equal to A into Ex the square into e to the power minus B by Ex. So now here these diagrams are showing like here the algebra diagram. The first thing is this one is like a flat band condition. This is right. So it's a band is constant, like where the phi, the surface potential will be between the interface barrier of height for the electron between Si and the SiO2. The second energy band diagram, here you can see what happened here is a positive bias, that is Vg is greater than 0, that is bias voltage is greater than 0, we apply positive to the gate actually. So electron will strongly will be inverted here, right? The electron strongly will be inverted here, correct? No, in this place actually be inverted, the surface can tunnel through the Si, this way. So here it will go like this, correct? Next thing is similarly you can say the negative bias. This is for your less than 0. That is a negative bias actually. When you apply negative bias, what will happen? The electrons from the N plus polysilicon to can tunnel through the oxide layer. It will tunnel through the oxide layer. So this only will give the gate oxide tunneling current. The same, this is interrelated with the hot carrier injection. See, same. So already we studied about this hot carrier electron, hot carrier injections. So the hot carrier injection in the sense simple, I can say, this is nothing but what I can say in the sense is like electron and holes. Electron and holes near the SiO2 interface. Here the SiO2 interface, this is the polysilicon Si. This is nothing but your SiO2. Correct now? This is SiO2. Interface SiO2 gain interface can gain sufficient energy due to high electric field in the short channel SC, short channel MOSFET. And it will cross the interference potential barrier and enter into the oxide. This phenomenon will be known as hot carrier injection because of lower effective mass. Because of the lower effective mass and the small barrier height, small barrier height will be how much? It is 3.1 electron volt for electron. Compared to hole, always the mass of the hole will be more, right? 4.5 electron volt. So the possibility of injection due to the electrons is more than the holes. This is called as hot carrier injection. Next is gate induced drain leakage. So this is I can call as GIDL, gate induced drain leakage. Now what will happen, the gate induced drain leakage? So simple here, when you are going to apply the high electric field, due to that high electric field across the oxide, so like between the drain and the gate I can say, but across the oxide, so your depletion region under the drain overlap region is created, so which will generate the electrons and the holes by band to band tunneling. Actually band to band in the sense of from valence band to conduction band, so that resulting drain to body current, from the drain to the body current only we can call as GIDL current. You can see this, they are saying, see the drain to substrate leakage. So that is what I mentioned. Drain to substrate leakage will be due to band tunneling current in the very high depletion region in drain overlap. So now here you can see this is the poly gate, right? This is the poly gate. This will be your N plus drain. So now as you know that when you are applying more and more voltage in the drain, or I can say due to the high electric field across the oxide, what will happen? The deep depletion region will be created under the drain, which will overlap the region is created because it will be created. So here this will be your substrate. Correct. See here, this is the drain, this will be your substrate. So now what happened here? So as it increases, see, this will be your depletion width. So you know that this portion we are showing here. You can remove that. So now from this I can say, like when you are going to apply the negative gate bias, like I see in this diagram I will show. See this, first here your drain VD is greater than 0, more and more positive. The drain current, that is VG, is less than 0. When you are applying VG gate at 0 or the negative voltage with respect to the drain, that is greater than 0 means like at VDD I can say, right, at 0. So 0, the N plus, which is the N plus here, this is the N plus you are having, here also an N plus. This N plus region under the gate can be depleted, you can see. This is what, as you are applying less than 0, your depletion region will be widened between towards, it will go towards the substrate I can say. It can be depleted and even inverted, depleted and it will be inverted. That is what we are showing here. But sometimes what will happen, the minority carriers are emitted in the drain region, minority carriers here, because when the VDD is equal to VDD, the minority carrier, this is what the minority carrier, the tunnel will be created, the minority carrier are emitted in the drain region under the gate. So as the substrate is lower potential, we know the substrate is lower potential always. So the magnetic carrier under the gate, so what will happen, the substrate is lower potential means the magnetic carrier at the drain depletion regions are swept away laterally to the substrate. So it will create a GIDL current, you can see. So this is what the GDL, see, this is what, like this it will get created. You can see the depletion region edge here. So one more thing I need to see here, how much ever you do, the depletion region will never touches the body, will never touches the body in the sense which will never touches the sub bulk. It is a bulk. Okay, so this is nothing but your GIDL. So there will be like the thinner oxide, this is oxide, thinner oxide thickness, and the higher VDD will enhance the electric field, and therefore we can enhance the GIDL current actually. So for low drain doping, because very important about doping also here, as I said, for at low drain doping, electric field is not high enough to cause the tunneling, because you should have the highly doping, you should have, then only you can the tunneling will happen. At low drain doping, the electric field is not high for a low drain. So that will enough to cause the tunneling. So at a very high drain, the depletion width and hence the tunneling is limited for high drain doping concentration. That is why we need to do the high drain doping concentration to avoid the tunneling movement actually. So that GIDL is worst for moderated doping. It is worst for moderated. Then when the depletion width and electric fields are both considerable. So this is about the GIDL. So here we are shown, okay, so this is your gate oxide actually. So here we will have, this is nothing but your gate, simple. This is the gate, right? And apply the electric field and the band bending or strong potence of VGD. The VGD is nothing but the voltage between gate and the drain, and the weak function of dB, that is voltage between the drain and the bulk. So this is your drain, you can see this. So from here it's going to drain actually. From gate to drain, that is why I can say it is like a gate induced drain leakage from the due to that oxide actually, or otherwise I can say due to low doping in the drain. This is something but gate induced drain leakage.